All right, the recording. So, some of you guys have experienced this in the tutorial already. Some of you have gone far and faced the problem with the inclined member, but not the uniform load. So if you face something like this, if you get spooked, again, you're going to panic, right? But what you should see here first is that, in fact, there are 5 reactions here, right? 1, 2, 3, and 4, and 5. Maybe 5 here. There are 5 reactions, okay? But then we have 2 internal hinges. One internal hinge will give you 1 extra equation, right? Because that's a location where you know that the moment is going to be 0. Have to be 0. So we have the sigma moment equal to 0 here, and sigma moment equal to 0 there. So we have 2 extra equations. So with 5 reactions, 3 equilibrium equations, and 2 extra equations, this structure is in fact a determinate structure. So the question is, how will you begin to attack this problem? Right? You can see that by taking the hinge and cut the free-body diagram there, because you know moment is 0, you can break this into 3 portions. First one is like that, and then the second one, and then the third one. Make use of the hinge. All right? And there you have it. So now it's going to be a bit tricky. How do we begin? Okay, so it's a question of experience, I'd say. If you have limited experience, in the sense that you have never practiced anything out of the classroom or the homework, or just problems that you do with your friends during the tutorial session, you may panic because you don't know where to begin. So when you see something like this, can you tell right away when to begin? Do you want to give yourself a few minutes to see if you can initiate the idea to attack it? Because honestly speaking, I don't remember when I began too. Because all I have just like, written like this. So I have to think for like 2 seconds because I have experience and it's my own problem. So I still have to think. Okay. I have to think about how to attack this as well because I don't remember. And so I think the most important thing here is to see if you can initiate your own idea, because once I tell you where to begin, you already jumped over that most important period, the initiation of problem solving. Now, why don't you give yourself a minute and see where you want to begin? Okay, you know that no moment here, no moment here. You know that. How are you going to do? What can you do to solve it? Give yourself. There's no wrong in this, okay? Because when you face a problem, I think that the most important thing is the first step, because you will not know where to begin. That's why you start applying your engineering knowledge. And now you have your engineering knowledge. Also, I hope. So, where you will begin? And you have the uniform load here. You have the uniform load here, and then you have the uniform load there. When you cut the free body diagram, you may, okay, you need to have some forces, right? Maybe I should put them apart a little bit. And now all you guys are doing is draw the uniform load on the structure like I just did, right? Come on, try to think about how to solve it. Now you have this. You have that, and you have moment. 3 unknowns there, and then the hinge. You know there's no moment, but there must be some kind of unknowns here. And then equal opposite. Maybe you should try to make it more common. I'm very cruel, see? Wow, right? So many unknowns. So where do you think we should begin?
Can we start at the middle?
Yeah, good idea, right? Yes, we can. At least in the middle, we know that this is symmetric, right? This piece that you cut the free body diagram through the internal hinges, this piece is definitely symmetric. So when this is symmetric, it means that you can solve for these 2 unknowns right away because they're symmetric, right? So that would be a good place to begin. We have 2 meters from the hinge, so that means this piece is 12 meters long. So that means yes, by taking symmetry, or if you don't see this, when you take the moment at the left hinge, you eliminate the axial forces, right? And then you can solve for the one on the right. Correct? Without noticing anything. You can take moment at this point, and then you can solve for the right reaction. And then you can take moment at the right point, and you can solve for the left reaction. Or you don't have to do it if you see symmetry. And right away, you know that this total force here is 12 multiplied by 1,000. So the total force is 12,000. So without further ado, you know this reaction is 6,000, right? The axial force is there, but you don't know because we have the external horizontal force. So it would be a great place to begin. So now you know these 2 are upwards. So this guy, you know, it's downwards, 6,000. See, you just need a first crack. Once you crack this, the rest is just, it will fall into place. So that's why I really urge you to spend a minute or 2 just to see if you can find the way to initiate your attack. Because if I tell you, it becomes, oh, okay, now I know. You miss the opportunity to apply yourself to the real problem. Okay, that's different. That's why people who don't practice, they would think, I understand everything. In the class, I listen to the instructor and I understand everything because you never experienced the moment where you need to initiate your problem solving by yourself. That's why you may think that you understand the exercises or examples and you should be able to solve anything. I would always say that you don't know what you don't know until you begin to do something. That's important. That's why we practice. So, okay, now you know, I don't need to finish this entire problem, you know. So the total force here, it's 2 meters, right? And then multiply by 1,000, so it's 2,000. You have 2,000 total force here, and then you have 6,000 coming here. So now you know that this is 8,000. Right? So things begin to unfold. And you know, I don't remember, but it seems like not many students, not as many students can do this problem the way I hope. And again, sometimes I get tricky without knowing that I am. Okay. So now you need to solve these horizontal unknowns. But you see, because of the presence of these forces, you can't assume anymore that because of your horizontal load like this, it will be equal on both sides again. Because you have the presence of these forces. So you have to take them. Okay. So I think we have to, before we move any further, we better give it some names, huh? Otherwise, it's going to be difficult. So let's call this A, B, C, D, E, and F. And let's hope that nobody erased my letters anymore. Okay. Sounds like a sneeze. My friend used to tell me, somebody try not to sneeze so hard that he or she broke his or her ribs. Because what you may not know is that the wind speed coming out of your nose when you sneeze is roughly 200 kilometers per hour. So when you want to sneeze, just sneeze it, okay? You don't, and it's the way that your body tries to get rid of something. Sneeze it, okay? If you want to prevent your sneeze, you may end up breaking your ribs. Okay. All right. And another thing, I used to read a magazine when I was young, and then they say, if you can open your eyes when you sneeze, you can collect the reward from the editor of the magazine. It's impossible because of the wind speed. So you can never open your eyes when you sneeze. Try it, but if you enjoy yourself, don't come to say that I do it to you. Okay, I just maybe you want to try. But if something happens, if something bad happens, it's on you, not on me. Okay? Anyway, so now we have the names. I can say we can. What? You can choose to take the moment anywhere you want, actually. You can decide. Anyway, let's say I'm going to take moment at point D. Okay? Sigma MD equal to 0. Now you have to be very careful. Now, this is where I take the moment, okay? Sigma MD equal to 0. Now we have this force doing the clockwise thing. We have this doing the clockwise thing. And then we have this doing the counterclockwise, and this perhaps doing the counterclockwise. Okay, so that's the equation that will give you the horizontal reaction at F or HF. Let's call that HF. So sigma MD equal to 0. Now we have 2000 multiplied by 1. That's 2000 multiplied by 1, right? Plus that thing is 500 kilogram per meter. 500 multiplied by the length, which is 6. And then again, we can use WL square over 2. Okay, that's the second one coming from this uniform. Then minus, I can use different colors so that you can see this guy, minus 8,000 multiplied by this distance now, right? 2 meters. And then, I don't know, minus, if you assume that HF is going to go that direction, minus HF, multiplied by the moment arm, which is the height now, 6, equal to 0. But it turns out that HF is not going in that direction. Okay. So if you set up your equation like that, you're going to get HF equal to minus 8 33.3 kilogram force, which means HF is actually pointing to the left. Crazy enough, right? So to the left. So I'm gonna change this a little bit so that you have a proper free body diagram. It's 833.3. And now I think when you've come this far, you will be able to use your sigma fx with a 0 and obtain this force. Okay, and the total force here is 500 multiplied by 6, so that's 3,000. And this is going to the left, so funny how that one is greater, so just add them up. So it's 3833. Okay, and then it gets transferred here as well, 3833. Okay, let you catch your breath a little bit. 0.3, so that you know. And that goes up, so that one comes down, 6,000. So you've reached the last portion of this structure, here, the left part, with all the forces available now. So now you have this piece, you see, with 3 unknowns, but you know all the forces now. Is there any question now? Ask me. You guys okay? You guys okay? At least tired, right? You know, when I was your age, I believe I was much worse than you. I could never study like these 3 hours, not impossible. And generally, I was never in the classroom. Because I remember in the second year, you know, I came in the classroom and I fell asleep throughout. Then after I woke up, I realized that sleeping outside the classroom was much more comfortable. So I started sleeping outside the classroom instead. And things kind of went downhill from there, you know. Anyway, okay, here we go. So now you know you can start filling in 6,000 here again. And now you know the total force is just like on the left side, that's 2,000. So now you know the vertical reaction here is 8,000. And now you got this one solved. You see, if you don't take the moment on the right piece here, you will not know the horizontal forces. And now you know, you realize that this reaction, this guy, is somewhat greater than the reaction themselves. That's the nature of the force. Okay, and the moment you're going to have to calculate. So to solve this moment, you may want to take sigma ma equal to 0 to solve for this fixed end moment, right? And now your moment is going to be equal to ma is going to be equal to 2,000 multiplied by 1 plus 6,000 multiplied by 2 minus 3833.3 multiplied by the height, which is 6. Okay, that turns out to be 9,000. Or this guy is greater, right? So it's ma is minus 9,000 from this equation. So that means, in fact, this is the right direction. Okay. So now, the rest is just a piece of cake. Because you know everything. So one job that is left for you to do is that you need to cut this members into two pieces. Otherwise, you will not know the moment at that joint, right? So this, you guys are catching up. Well, I'll take a little break. You have never met anything so easy in your life, right? This is really easy. So, okay, you ready? Ready to move on? So let's wrap it up. This piece, if let's say if we do not pay attention to the actual load, if we just want to draw the shear force and bending moment diagram, the fact that you have two internal hinges here on the left and on the right simply renders this piece into a simple beam, isn't it? Because the moment at C and D have to be zero, both. So essentially, this is a simple beam. So I don't draw shear force diagram, bending moment diagram for you, okay? And you shouldn't be upset by that. No, the instructor doesn't draw the shear force and bending moment diagram of a simple beam for us. We're gonna protest, right? Anyway, let's focus here. So I'm just gonna redraw them on this page. So now you have that, and then you have that. Excuse me. Okay. We have 6,000 here. And then we have the axial force. Okay. And then we have the uniform load. So, you get this moment, right? There must be moment now because it's a rigid joint. So that's MB, right? MB is simply 6,000 multiplied by 2. Because it's the length of the member, right? You can call it's 2 meters. And then plus the moment from the uniform load, which is like how much? 1,000. Multiplied by 2 square over 2 again. Which is 14,000 kilogram meter. It works pretty well. This because the microphone is at my mouth level. You don't have to hold on to it anymore, right? Any question? So this is how do we call it? BC, right? That we're done. And not really, but we need to complete this. So this is how much? It's 6,000 plus this total is 2,000, so that's 8,000, right? And again, we have the axial force, another 3,833. Now that's complete. And again, wrong plan. I'm gonna move that a little bit too close. So we have the force coming in from here, 8,000 downward. This one goes to the right, and this goes to the left, which match with the reactions, right? And then we have the moment here, 9,000. Oops. Okay. And you have the moment coming in from here. 14,000. So you better pray that they give you the proper equilibrium. Do they? So if you want to check 14,000 minus 3833 multiplied by 6. Oh yeah, that is not that's number. It's the other way around. Okay. Yeah, I should write the opposite. Okay. So it's 9,000. Right? So yeah, we good. And I believe you can finish your diagrams by yourself. That's AB. And next one, when you've come this far, you should realize that member BE is exactly similar to BC, but the mirror image. Correct? So I don't bother with BE. Yes.
I think moment 9,000 is negative 9,000. That you have calculated.
That's why I swap the equation. See?
Oh, then we have to swap the direction.
You know that I have to say my apologies because I don't really pay you know the utmost attention to the direction because you can feel it. You know, it's good that you bring it up because when you see this number, it's greater, right? Let's say 4,000 multiplied by 6, that's 24 something. This is a moment. This moment is trying to move your structure to the right, right? It's clockwise. But then this guy is trying to move your structure to the left. And when you know this term is greater than that, so the end result here of the moment is that your structure will be moved to the left by this horizontal loop. So that's why we need the clockwise moment to try to counteract that movement, because the way your horizontal load here is pushing the member AB to the left, it will generate the counterclockwise movement around point A. So yeah, I don't, because I've been doing this like for years, so I don't really start off by sigma MA equal to 0 and okay clockwise positive, that kind of thing. But if you want to make it right and you say okay this is clockwise, if you want to make it right, you may want okay sigma MA equal to 0 and clockwise is positive, so you have like 9,000 minus 3833 multiplied by 6 and then minus and then plus 14,000. That's going to be the correct one, right? And then this is 0, right?
Yes, sir.
Okay. So you can do this, you can do this. There's nothing wrong in it. And maybe not looking cool is not wrong, If you have to make it correct first before you have to make it cool, all right? So make sure that everything is correct. Then you can worry about being cool later, right? Good, thank you. All right, so we have because we started off a little late because of the force majeure, as we have mentioned. So we have I would like to continue on for a few more minutes, but I will not be able to complete this. But again, I think we have a clip solving these two supplements from the previous year. So what you can do after today is that you may want to try to solve this by yourself. And then if you can't, just go and look at the clip from last year. because the solution is already there. We don't have to finish it. Okay. Anyway, DE here is similar to BC, but it's just the mirror image. Okay. So that means I can focus on the EF. If it's similar, I should have 3833 here, and I should have similar, but it's a mirror image, right? That's the moment, and one goes up, so it should come down with 8,000. Okay, and then you, of course, you have the reactions. And don't forget that you have the external here. This is 500 kilogram per meter, and that means somewhat your reaction here is. Okay, so that's a complete free body diagram. Now, like I said a moment ago, you can try to complete your shear force and bending moment diagram by yourself, and the solution is there on the clip from last year. Okay, and now you've come this far, it should be a piece of cake, you know? So I'd like to spend a few minutes with the last example. In fact, it's nothing really. It's just a classic example that I used for a long time. So I just wanted to include it. Okay. Let's wait for a minute. You should be able to do the diagrams in your sleep now, I suppose. Sleep, you can maybe. Okay, so are we finished with this one? Okay, let's move on to see here a little bit. Okay. Actually, this one is nothing difficult at all. Just the same old thing again and again. But the reason that I wanted you to have this is that this is a true wind load. You know, when you have a warehouse or factory with a shape like this, when you need to do the window analysis, this does occur. Because when the wind blows in here, what happens is that it's just going to hit the building on one side, but then it's going to create what we call suction. It can suck up the building like that from the wind pressure. So this load is true. I just want you to have one condition that, okay, that's why we do structural analysis, because it actually happens. And when the wind comes in here in the real world, you would have to know the location of the project that you will build, and then you can acquire the information about the wind, such as the wind speed that you would have to take care of, the terrain effect, so whether or not it's like an open space or it's a space squeezed between the buildings, that will have impact on the wind speed. And then when you pick up the wind speed, because somebody already collect this kind of data for all of us, so there's a data of wind speed throughout the country. So you go and look at the building code, you pick up the wind speed, and you can calculate this pressure or the load from wind speed and some other factors. So then you can start applying this load on your structure. Okay, so this is real. All right, and when you face this problem is nothing because all the uniform load are already perpendicular to your member. So it presents a little problem because how do you calculate the reactions, right? That's just the thing, the only thing. So now this time you need to be aware of the fact that, okay, now you have this load in that direction and in that direction. Oops, sorry. In that direction, so it means that when you want to calculate your reaction, you may want to, break this into this component and then that component. And now you can use the resultant. And then for this, goes on like that. So you may need to break this into this component and then that. And then you can start taking the sigma moment, in the very conventional way. And then you got the reactions. Then the rest just follow it. Okay. So let's say we still have a few more minutes. So let me give you a full experience. So let's call it A. Okay. You can take sigma MA with a 0. And then, this is like, now you have, okay. The first one is 300 multiplied by 6, right? And then multiply by 3. And then the second one, this is not our favorite 3, 4, 5 triangle anymore. That's 3, that's 6. So here is 3, here is 6. That it's 3 square root 5. And this theta here is 26.57 degree. That's Celsius? I don't think so, right? These degrees are actually unitless. Oh, degree is a unit already, right? Not unitless. But the radian is unitless. Okay, so when you have that, now I can write easily. Now you can look at this. When you take moment, you better be careful. Now you have the horizontal component and then the vertical component. If this is the angle, that is the angle, right? And that is the angle. You see, if you draw things on scale, the size or the magnitude of the angle, they can tell which one is the angle that you should use, right? If you pay attention to your drawing properly, it should help. So we're gonna have the sine one is a horizontal, okay, plus 150 sine 26.57. So this sine one is this. Right? Multiply by the moment arm, which is now 6 plus a half of that, so it's 7.5. That's where the load is, right? Okay. And the cosine one, it still gives you the counterclockwise. So plus 150 cosine 26.57. But this time the moment arm is half of 6 here, right? So it's 3. But this one is in fact that. Okay. And the next is this component, right? This guy. Now the vertical is giving you the counterclockwise, but not the horizontal one. So this time is going to be minus 150 sine 26.57, right? Oops, sorry, that's one. No, that's 350. Sorry. So. Okay, this time multiply by the same, right? Because that's a 7.5. Then plus the vertical component. Maybe I should okay, do some, right? This is the guy, right? Then plus 350 cosine 26.57. This time multiply by 9. This is that one. Okay, and then another one plus 475 multiplied by 6 multiplied by 3 and plus the reaction, let's call that A, B, C, D, E. RE multiplied by 12 equal to 0. So yeah, once you solve the reaction, the rest should be okay. And you do the same to get RA. Okay. And one more thing. The challenge is that you look at the point C here. Wow. If you cannot work your way from both ends, you're going to have quite a challenging problem to transfer the force from member BC to CD. Because it's like a very two different angles, right? So it is a better idea to work with member AB and then BC and then DE and then CD. And see if you can have the same moment at point C. Okay, this will be a good exercise. This one, it's an example that I use every year. So if you don't want to watch the clip, you can maybe look for the whole lecture. You'll see the division have it. Okay, so that's it for the frame. Sorry, we are running a little late today because of the hiccup that we had in the morning. So I don't want you to miss this. Okay. And actually, I did not plan to use the supplement. And I thought, wow, I was pretty quick, teaching online. That's why I add 2 more supplements. If it was before the COVID, we only have like 2, 3 examples for the frame. Now you guys have 5 or 6 because I write on the iPad. It's much quicker. Right. So yeah. Tomorrow, again, as usual, the active session, right? Yeah, as usual, and you guys should work on the the incline member experience tomorrow, and that's the end of the frame. And before we go, this will be in your midterm exam up until this point. Next week, we are going to start something brand new to your engineering world. It's nothing to do with this anymore. And what we begin to have next week will not be in the midterm exam number 2. It will be in the final. This is up until this point. It's for your midterm number 2, and we're going to have that according to our schedule. Okay, we can discuss next week whether you want to have the on-site exam or online exam. But on-site, we need to prepare a lot. We need to find a group. We need to make the copies of the exam. Yeah. Okay. So that's it for today. Any question? Guys at home, folks at home, you're free to leave now. The class is over, and you were here too. You are free to go. If you don't have any question and you don't want to hang around, I'm gonna submit.